day. Thank you very much for the invitation to present today at the Mars Society Convention. I'm happy to show you some Mars architecture projects we did at the Technical University in Vienna last semester. Let me share my screen with you. So I hope you're able to see the screen. My name is Sandra Häuplik-Meusburger and I teach at the Technical University in Vienna, Austria, and the TU Wien is one of the largest architectural departments with over 6,000 students. Our department, Building Construction and Design, has a clear focus on construction materials and technical integrations. At our department, we also offer a regular course in space architecture. The usual studio starts with intensive preparation, analysis and research, because very often all the physical conditions on Mars and other planets, for example, are very new to the student. In order to get the most knowledge within the available time, students are grouped into small teams and given a research topic to study, condense and then present to the whole group. In addition to self-study, the 3-month course is designed to include a number of input lectures from renowned space experts and professionals. Sometimes we have the possibility to actually build the projects that we develop. In 2013, students, for example, developed 3 one-to-one prototypes that were finally tested in the Sahara Desert in Morocco by the students themselves within the Austrian Space Forum Mars mission. For this project, we started, the starting point were potential emergency scenarios during EVAs in order to design the deployable emergency shelter for Mars. As a preliminary result, 9 critical situations were considered highly relevant for extravehicular activity. The first one is unconsciousness and breathing, and the second one is not unconscious but not breathing. Then we have one, astronauts get exhausted and have to rest for a while, and many more. Then students developed their first concept based on the requirements coming from the medical scenarios. The broader concepts ranged, for example, from flexible spiral systems on top to the applications of folding techniques, you can see on the right side, and folding techniques and with scissor-like elements with automatic deployment. The model you can see on the left side. And the integration of the shelter into a human transport vehicle. Finally, we had the possibility to build the prototype and test it during the field simulation in Morocco. In general, we have conducted a number of space architecture design studios, and you can find all the results of the past studios online on our ESO account. Please check it out. In addition to coordination of those studios, my personal research topic is space architecture in relation to habitability in extreme environment. We have just submitted a new book on habitability, for which I worked closely with space psychologist Gerald Bishop. It will be open access and out this year. Here is another link for you. Besides my work at the TU, I'm the academic director of the Science Academy in Lower Austria, which is a unique and wonderful opportunity for 14 to 16-year-olds to learn about all kinds of topics of space. The curriculum takes 2 years, and we have just started a space club. Please have a look. The Mars City Design Studio this year took place from March to June. During this time, 12 projects have been developed and elaborated by the students. As usual, We started the studio in the beginning of March with input lectures, and we discussed relevant topics for the design of a Mars habitation project. Topics included basic information on Mars characteristics, environmental challenges, science opportunities, and of course past, current and future planned missions. We know how we require technologies, especially for habitation design, that includes thermal control systems, power supply, energy storage, shielding and maintenance, to name a few. Of great importance for remote and extreme environmental habitat on Mars, crew and life systems and in-situ resource utilization became more important. Each student team researched and prepared their presentations on selected themes in order to present it to the whole group 2 weeks later. However, shortly before the next meeting, the course was switched to distance learning due to COVID-19. So this course was the first course that we ever held as an online studio, and this is a picture of the first online meeting. It was challenging and all of us had to adapt to this new situation. The topic of the studio was changed in that together with the students, we decided to work on a more detailed concept for a city on Mars. And the approach of the studio was to translate their vision and what they would like to see in a future city on Mars. So I had asked them to first think of how do you think would the future city on Mars look like? What would be needed in order to realize this distant dream? And then I have asked them to think of what would be the first base necessary to realize what you are envisioning for Mars in 100 years. This was a bit of a twist of thinking, and it was a surprise for the students and very challenging, but I will show you some projects and you can see the futuristic idea they have, the vision for Mars City, and then how they would start with the first Mars base. Overall, we have developed 12 projects in different Martian locations, mimicking a possible future network of settlements on Mars. During the whole semester, we could only meet online, and some of the students were spread around the world. Some of the students got up early in the morning to join the sessions, but we met regularly and all meetings were open. Similarly to the normal studio, students could listen to all the other students and could ask questions about their project presentations. Often we had guests from the larger space community with us, and usually the guests started with an input lecture followed by an intense project discussions with the students. Another change due to COVID-19 was that I asked the students to reflect on their self-isolation. Being stuck at home can be challenging. Isolation, boredom, and living in a small space with a limited amount of people are only a few of the challenges each of us is facing and has been facing during COVID, and the students were asked to create a short video documenting their personal experience from an architectural point of view. How did you overcome it? Which ones could you handle? What was the biggest challenge? And what do you think would help in terms of architecture and design? This reflection helped them even more to develop their future visions for a Mars science city. Eventually, we had 12 projects developed, from which I will show you 3 now. This project is called Moving Mars by Armin Ramovich and Jim Schneider. It is a mobile rover project that shall connect other bases with each other. The team designed the rover as transportation to move people and cargo from one place to another on Mars. The rover has the option to have additional models attached for research purposes. The group calls this lab on the road. In principle, they thought of a traveling mode for maximum 4 days, a moving mode for maximum 2 days, and a steady mode. Of course, the rover was designed for autonomous driving. It is spherical in shape in order to change direction easily, and with the additional wings to have the possibility to move in horizontal position on uneven terrain. The habitat consists of a multiple inflatable structure with an airlock among each other. The airlock can be an additional event, or as they envision that many their bases have bigger docking stations for the rovers already integrated in their shell. This is the project Dune by Sahil Adnan, Kaitlin Podwalski, and Julia Ferrara. It is a far-term visionary image of the group, as I had first asked them to think far into the future and design a life on Mars they would like to see. Dune is a concept that draws from animals living in the harshest of environments, such as the desert. The concept aims to take advantage of Mars' harsh climate and sandstorms. The structure is designed to have a shallow pitch roof that is faced windward to collect the dust and use it as a natural defense to the severe radiation. This helps limit the use of materials by advantageously using the surrounding environment for its protection. Dune uses the natural forms found in the surroundings in its design to seamlessly integrate into Mars. Dune also attempts to integrate new technologies and natural ancient geometry using the regolith deposits and plastic design structure. They will use polyethylene shells as the main building material in order to be able to recycle it later for other purposes. The group assumes that it is possible to manufacture high-density polyethylene polymers on Mars using carbon dioxide from the atmosphere and hydrogen from water in the soil. With 3D printing technology, a structure that minimizes construction and maximizes light and space can be built. Dune can begin as a small infrastructure and gradually grow to a house, an entire Martian city. The first mission will deliver the cargo and the rover to land on Mars. The swarm team, rovers and 3D printers will then begin to work on the base of the minimal configuration habitat. The inflatable, which you see in the core and the middle, is set up, and then the shell is 3D printed around. Then the first cruise is estimated to arrive in 2068, and all further missions in the years after will benefit to the infrastructure and the expansion can begin. The next project is called Atlantis. It is based at the Shiseido crater, and instead of a predefined master plan, this group has an expansion system proposed for the realization of a city on Mars. These are the system elements they propose: a small green element, a crew module for the first mission, a base research unit to complement the first habitat, a connector unit, a large green unit for food production, and a workshop and medical unit. According to population size and the capacity of the modules, an algorithm will calculate the number of needed units and will lay out possible further developments. As the settlement grows and the needs of the settlers change, modules will align differently around connector units according to the needs of the crew, the sent infrastructure, and the topology. They will create different areas and meeting points for the inhabitants. The first preliminary habitat is packed and has a diameter of 6 meters. When deployed, it will be about 16 meters. Actuating systems are used. There is a foldable floor, a vertically sliding steel core, and an inflatable membrane. The first actuator is the unfolding origami floor, to which the 3 casing parts are attached to. The second actuator is the sliding core. It moves vertically, doubling in height. The frame holds the core units that contain sanitary fittings and small plant system. and the cupola with water tanks on the top. The third actuator is the inflating membrane. Pressurizing the interior of the habitat is essential for the survival of the crew members. The pressure will also act as main load bearing. Keeping it minimal, functional, but comfortable. The main goals of the design was the isometric connectivity of the expansion. It can be seen within the habitat. Sanitary fittings open up towards the private rooms. There is a division between private, social, and more public areas. The kitchen is oriented towards a larger area for intimate socializing and medical treatment. The research area is on top of the private rooms to make use of the vertical design. This way, loud and quiet, social and private space is separated. The area between the private rooms can be used as storage, recreational and training space and is as buffer zone at the same time. The radiation protection is made of the exterior layer of the enclosing membrane is equipped with chambers that are filled with regolith. And a 3D sintered regolith will be printed over the habitat at a later stage. This is an interior that the group is envisioning for the first people on Mars to live in. It's the social area, the connecting space that connects private and social spaces. And with this slide, I would like to thank you. And please check it out. Have a look at our online publications. You can really find all projects and the whole project documentation on our ESO account. Thank you very much. I hope you had enjoyed this presentation, and thank you very much for the invitation. Thank you very much for the invitation, and it was a pleasure to be part of the Mars Society Convention. Goodbye.